All right, today we're going to talk about chemical families. So here's the deal. I told you the periodic table is the world's greatest cheat sheet. That's because all the answers, or at least most of the answers, can be found on it without too much effort at all. What do I mean by that? Well, when the periodic table was first being founded, they didn't have any of these numbers to play with, or at least had very few of these numbers to play with. So they were things like oxygen having 8 or whatever. They weren't really doing that. Instead, what they're doing is they're going from lightest to heaviest. So hydrogen was clearly the lightest. Helium, when they found it, was less light, and on to get heavier and heavier things. Now, what they did know is this: certain things reacted the same. So, for example, on this far right-hand side is helium, neon, argon, krypton, xenon. Now, helium, neon, argon, krypton, xenon all have a similar set of things when you put them in chemicals. That is, they don't do anything. They're called noble gases because they don't do anything. By that I mean, if you take helium and you add it with any chemical in the universe, at the end of the day you have helium and whatever that other thing is. It never makes a chemical reaction. Refuses. Straight up refuses to make any sort of a reaction at all. It says, well, not going to do anything. If you want to put out a fire, any of these will work beautifully to put out a fire. Now, you've probably heard in the news, hopefully you've heard in the news, that radon is a gas that could kill you. Like, aha, these other ones might not hurt you, but this radon thing will kill you. It'll kill you because it's radioactive, not because it is chemically active. In fact, the problem with radon is it doesn't smell, taste, or do anything. It doesn't change the color of your wallpaper. It doesn't do anything. None of these do anything. And so if radon is in your house and you're breathing radon right now, you would never actually know you were breathing it. Because it's radioactive, that can kill you. Helium, people suck it in at parties. I don't recommend that because there's a chance you could not expel it properly. But if you do expel it, it comes out as doesn't hurt you at all, right? Makes your voice really high. If you do the same thing with xenon, it makes your voice really low. But the same thing, you wouldn't taste it, smell it, whatever. It just simply, you can suck it into your lungs and get it back out. Again, don't recommend that. It's probably not a good move. Okay? Another example is this group right here. So let's say stack the ones that had similar properties in a column, right? So I'm going to take you out to here. This is copper, silver, gold. You should know copper, silver, and gold because they're precious metals. Why are they precious metals? Because a long time ago, when you were ancient man, you needed to make money out of something. You needed something that people couldn't cheat you on, something couldn't manufacture in their backyard. So, for example, there were people that, took stones and they made holes in the middle of them. Aha! That was money. The problem was I could go outside and get my own stone and make a hole in it, and that's fine. See, something that's relatively rare and easy to keep track of. So, for example, copper, silver, and gold all have the same properties. What are the same properties? They are metallic. They're all metallic. They all can be with a hammer and a good set of tongs. You can cut them all into shapes. You can pound them into a flat shape. They don't rust very well. So meaning that if you have one of these coins, if you make one to a coin, it doesn't rust very well. They're hard to find. So you have all these properties to make a good choice for metals. Now I'm going to take you over to this far side over here. Okay, hydrogen you're familiar with. That's the stuff that was in the Hindenburg. That's the stuff that causes fires and whatever else. Once you take a look at this rest of this list, you're going to get to watch 2 videos, which if you actually watch them all the way to the finish line, you might enjoy. Okay, this is lithium, sodium. Remember, this is lithium, sodium, potassium, rubidium, and cesium. These were put in the same family. Why were they put in the same family? Because they have similar chemical properties. What do I mean by that? Here, we're going to watch a video. This video is put together by a guy named Scott Milan. I'm going to let you watch it from start to finish. On the left, there is going from left to right is lithium, sodium, potassium. And he's going to take them and he's going to put them in water. Same thing every time. All right, so here we go. We're going to watch this thing.
We're working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light.
Keep watching. You're going to want to see
The other
this.
side's pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut.
He's cutting metals with a knife.
So for the potassium, this is the side that's been freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water. So here I'm going to take the lithium, add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium. So I'm going to put sodium into the next one. The sodium is probably going to ignite. You'll see some orange flame perhaps, or some sparks, or some shrapnel. And then last one, I'm going to go ahead and put my 2 pieces of potassium in. This is less potassium than the other two. In terms of amount, you'll find that the reactivity is a little bit greater.
Now, he didn't like what happened with the sodium, so he's going to try sodium again in a second.
Now, that potassium there was quite reactive there, but the sodium sometimes will allow hydrogen gas to build up. In this case, it's not igniting. We can try adding another piece here. We can hope that that's going to go ahead and actually send off some shrapnel and flame.
Remember, this is just sodium and water, nothing else.
All three produce hydrogen gas. All three produce hydroxides. There's your alkali metals. Next, we're going to go ahead.
So that is what you have when you put sodium, lithium, and potassium. You can see why they put them in the same place. This leads to another question. There's more things on my chart. So you put lithium in there, and here's lithium, right? He put lithium in there, he put sodium in there, he put potassium in there, and you're thinking, well, each one of those you just drop in water, it explodes. What would happen if I did like a bigger chunk, or what would happen if I did rubidium or cesium or francium? Well, there's a video for that too. It's put together by a guy named Ryan Mullen. Ryan Mullen, here you go. There's no audio to this, so I can talk over it. Big chunk, see the chunk hitting the lake? Sodium, by the way. Just a metal rock threw in the water. Potassium, that'd be bigger. Ooh. Little tiny chunk. Ooh. That's cesium. So what's the point? Remember, of course, this is the greatest cheat sheet ever, right? If it's the greatest cheat sheet ever, then I should be able to figure out what the various properties are. So as I'm looking at this, and as you start to do the assignment you're about to do, you should remember that as you go down a column, manganese is going to act like molybdenum, which is going to act like tungsten, which is going to act like seaborgium. These all have similar properties. And so you're going to expect them to act the same way. Okay? So they have similar properties. Now, not all of them are exactly the same. They're not. Boron and aluminum are not perfectly the same, but they have similar properties. Does that make sense? And so that's where we'll leave it.
Today, your information is